Like, LinkedIn.
There we go.
Okay. Um, Thank you so much, Laura, for the lovely introduction and for organizing this as well. By the way, where did you get that introduction from? Did ChatGPT give you some notes or?
No, I
Oh,
wrote it
oh my
myself,
God, it's
but
amazing. Can I
I did
guess it?
stalk you on LinkedIn.
I guess that because it really, I don't have to introduce myself. I had one slide that was introducing myself, and yeah, you did it beautifully. It's um, I couldn't write that better myself.
I'll
Yeah.
forward it to
So if you
you.
could forward it next to me as well, that would be nice. Yeah, later on. Okay. Thank you so much. It's a pleasure to be here. The reason why I'm here is actually Julian and I, we're exploring a potential to write a WEAF, NVO, and a DFG grant. And yeah, so it was an opportunity for me to present some of my work as well and for us to further discuss some of the ideas that we have with this sort of collaboration. So the We Run really tries to see if we can connect our ideas together and get funded for some PhDs and a postdoc position as well to continue the shared interest in our line of research. Yeah, so today I'm going to cover a little bit of how I'm approaching multimodal MOBI approaches in my work. What are the struggles that I've really um, come across, and how we sort of can move ahead with some of my ideas and the line of research that I envision as well. So I'm ready, you know this. I was born in Singapore, and I did all my adult life and my studies in South Australia, Marie Curie, etc. And now I'm tenured in U20. When I was doing my Marie Curie fellowship, I was working under Professor Willem Favai, which Edmund works with quite a lot, and also Stefan Professor Arnold as well. Yeah. So my outline today is covering 4 points. The challenges in model sequence learning to give us a broad sort of overview of what is going ahead. We already know a lot, but what can we do towards creating individualized approaches? Some The next is noise and nonlinear dynamics and how we can quantify some very interesting aspects of motor learning and in general, and how we can learn further about the mind and the body in its learning performances using the MOBI technique. So just to define what motor sequence learning is, it's a process in which we acquire the ability to perform a sequence of movements, and over time of repeated practices, we get better at it. So think about a pole vault, right? Really complex. You can see in some of the images here, a surgeon nowadays performing minimally invasive surgery, shifting a key, tying shoelaces, etc., playing a piano. So a lot of things that you think, or even coming to work, the way you take your car and a route, it's a sequence, and you're performing a motor sequence to drive all the way here as well. It's embedded in our everyday lives, and we don't notice it. Yet it's fundamentally important for how we do things every day to be successful at them. So we have these complex motor sequences, dance, working with drones, surgery. And yet, if we talk about the gold standard of coaching, it's really one-on-one aspects. And this is very, very intensive. It's time consuming. And there's also poor objectivity because quite a long time ago, Yerkes Dodson solved the U-shaped principle of where we can find the optimal point between arousal and performance. It's been sort of elusive in quantifying it. So it was sort of made popular again with Guadagnoli and Lee in the human movement side of things, of trying to find this perfect challenge point to engage the learner such that they have the most amount of acquisition. They can learn the maximally, they can gain that amount of performance where something is not too difficult, where they give up, or it's too easy that they just sort of do it in a haphazard kind of a potential. So it's quite elusive trying to get this. How different researchers have quantified it, how we've used different measures, the measurement techniques have improved, but we haven't really got more precise. Although the measurements have improved. So yeah, there is a discord in the theory and what's applied. We take very, very Yeah, I'll talk about this in the next slide actually. But we haven't been able to standardize what we consider as challenge. And also, we have no consideration of the mental states that are in there, especially in the human movement literature and physical ergonomics as well. The body is the body and the mind is separate as well. So in the end, we get suboptimal results. However, I think that there is a lot of opportunities for impact, and I've been trying to explore some of them to derive what I consider as more precise, more what we call effective and efficient individualized training. And the 4 points that we can consider is, firstly, you can consider the task itself. What are the boundaries? What are affordances around the task itself? You can vary the difficulty in the task. So that's one aspect of challenge. The second is that in my previous work and also currently, I look at what the mental states of the person, the learner is at. In the past, I've shown that mindfulness practices, mental practices like mindfulness, can alter the way the cognitive function operates and acquire or learn in a different manner. Therefore, sometimes it engages and allows them to learn these modal sequences more effectively. And also, we can leverage on the last 10 years of where we've gone with multimodal brain and computer interfacing. So we can now measure full body movement, moving around with a lot of cleaner brain signals. We should be able to leverage on that as well to be able to target and provide the individualized training and also the functional task difficulty, which is the environment that's around the person, the learner. So what is the person learning in? Is it a stressful environment? Is it a non-stressful environment? Can we train that aspect of dealing with the learner itself? If we take this and we talk about that, I think it's a lot more precise than what they only consider in the literature as nominal task difficulty. Because that's the easiest way in the past they've been able to engage how much practice someone gets, change the target size, and they ignore the rest of the other 3 aspects. So I think this is a more holistic model. And I will present some of my work in working towards how we can get this precise individualized training. So modal sequencing in the lab, all right? We've had this for the last 20 odd years, and we use this to inform of our theories, right? The task that I've been working with the last 4 years is the discrete sequence performance task that was designed by Willem Verwij back in 1999. And we sit there at the keyboard with our fingers on that to respond to 6 to 8 different stimuli that form a sequence. And over a repetition of between 5 to 1,000 different sequences, you start to get a point where it's overlearning and you're able to predict what's coming up already. So often after 500 and 1,000 sequence repetitions, by the time you see the first signal over there, you know exactly what's going on in there. And what's coming up in the next 4 to 6 different positions as well. The way we also try and understand how much learning had occurred is to introduce a test phase of a new sequence. So often we put in a new sequence, the transfer block, and we look at the differences between the response times to understand from the point of the last learning of the old sequences and the point of the RT of the new sequences. And this is thought to reflect the amount of ongoing cognitive processing and resources that's required to acquire those sequences. But we really need to move from that because there's so much of our body that we do on a daily basis that encompasses different limbs, movements, combinations of the legs and the hands. I said, look, we have to get out of that. So the last 3 or 4 years, I've been working on moving that to a more ecological version. I would not say this is perfect, but it's a step in where we can have something a bit more control rather than just having a lot of free naturalistic tasks and you just measure. A lot of researchers do that, but it's hard for them to quantify whether the existing theoretical frameworks still fit onto those tasks as well. So here's an intermediary step. I converted that task into a whole body movement. So you can see someone here on front of the mat. It looks like the arcade game in the game box over there where you put in your token and you're dancing. But we can control every aspect of it, like how many stimuli the timings of the stimuli, the accuracy rates, the RT, and the preparatory periods as well. So it becomes interesting because here everything is controllable for me to test whether existing frameworks that we have still transfer onto a whole body version, right? Because once you start to change the way it thinks, sometimes those theories don't still hold through, okay? And we'll get to that in the second half of my talk as well. So yeah, the need for more naturalistic tasks, and also the methodology is in print at the moment. I'm doing the proofing at the moment, and so if you're really interested, you can search that up and download the entire methodology of how we are doing it. The difference is that the ones that Professor Fawai had done is a continuous task. So whenever a stimuli pops up, you perform it immediately. Whereas this version is a go, no-go version. So afterwards you see, but there is a screen that that's shown the sequence first, and then they pause for 1,000 milliseconds to wait for a go or no-go signal, because it's just to keep them engaged with it, and then they have to reproduce the sequence as well. Let's see how it looks like in the block. So this is one of my students who is performing the task, and you can really notice that he looks at the sequence, and then he has to pause there, and then there's a go signal, and he doesn't look very engaged, basically. He's not very participating very well. But by the time they go through 4 blocks of learning, this is how their performance looks like. So they're a lot faster. The way they engage with the task, where the eyes is looking at here is looking at his feet here. He's also looking at his feet, but he's already sort of anticipatory. You can see the changes in the body posture. So one block is usually 48 trials of 6 steps. And by the time you perform 4 blocks, that's about 1,115 and 192 trials. And most have already mastered the 2 different 6-step sequences by the time they reach block 4. One thing is, people are always very surprised when you look at the RT performance. It's not very different. So we can get average RTs around 300 to 400 milliseconds, and the key press versions are around 200 plus for the fastest learners. So here you can see that the body also has its own way of optimizing the sequence itself. So I want to talk about this part. So we know the task now, we understand how it looks like, and we want to use our understanding of nonlinear dynamics to be able to quantify how learning occurs. And I'm always very interested especially for me, I consider my guru as the Soviet scientist Nikolai Bernstein, who firstly outlined this whole idea of repetition without repetition, or how does the body really organize hundreds of degrees of freedom to be able to repeat something with a lot of accuracy. This came from his work of a lot of those steel workers, of why this elliptical form of hammering the nail onto the task itself often has a different form every single repetition, but at the same time, they're always able to accurately hit the nail onto the board as well, you see. And what's very interesting is we often consider this kind of variation as noise within the motor system. So that's something that we need to explore, because there's this balance between whether someone is exploring or optimizing the motor movements that they're performing at that time. So there is some complexity in variability, and you can see this regularity as well. Nick Sturgill from Nebraska, Omaha, often considers what we consider as pink noise. So if there's some sort of regularity within, and it's not totally random and chaotic. So for example, the first graph that you see over there, these 2 examples have the same sort of mean and standard deviations, but the top one has a lot more differences in the peak in its variation of regularity compared to the bottom example over there, which has your PQRS of signal very, very regular in its things. The mean and standard deviation can will give you the same conclusion. But when you start to look at the time series data and the structure of the variability, the complexity is different, you see. So how do we quantify this? How do we be able to understand whether something is random and chaotic or whether something has structure, and that pink noise is a sign of a healthy regularity or healthy variability within the motor system itself? Another example that I like to look at is, of course, the structure of your lungs and its alveoli spreading out, or the Romanesque sort of plant over here. Then in every single structure, you have a repeating element of the entire structure as well, you see. Not every one of them is identical to each other, but the variation of it leads to a combination where there are smaller structures, and that whole small structure leads to larger as well. So we can call this, and we can say this is fractal in a sense, okay, that there's self-similarity that's evolving in there within the structure. Maybe this is not something that's new, some of you are already working with this, but we need to be able to quantify that. So whether something that's fractal is actually useful and helpful for the learning of the person as well, you see. Here's an example that I draw a lot on from the Charmé and von Americh's work, in that they use a split treadmill in which they were able to measure the preferred speed of the gait of a person, and they changed one side into half the speed of the preferred gait. So where you can see that they use a 1/f fractal scaling exponent, and those participants who are closer to the 0.9 aspects form these trough, right? It's a quadratic sort of element in there between the right leg and the left leg. And those are hovering around 0.9 to 1 are really much more fractal and successful in performing this perturbed asymmetrical walking, you see. So they are ones that are able to regain most of the symmetrical step performance compared to the other participants in there, where either side of it, where it's too little, is chaos, on either side, or too much as well, is chaotic, and they're not able to deal with the task itself. So the Hurst exponent is one that I use that is a variant of the 1/f scaling, and we're able to quantify some of these challenges. Now, when I first did this task, this was one of my earlier experiments, I really didn't know how to make understanding of this data, because whilst we told the participants, look, perform as fast and as accurately as possible, we wanted some level of, there were many ways to do it. You can tell the participants to use a certain foot to the certain task as well, to the certain direction that is. So let's say if I say right foot goes to the front, you can fix that. Or you say left foot goes to the left, like that, you can fix that as well. But we wanted a naturalistic approach whereby they are able to formulate the strategy on their own. Then we want to quantify and say what is making these people more successful than other people, you see. So this is one of the earlier data sets of one of the participants that was a very good performer in terms of their response times. And I just want to show you a video. See if you can pick up just based on that, what's happening in there. This is in the accents, and I'll give you guys a bit of a... So this is someone from the past, yeah. There's this burst of activity when they perform the task, and this is in the z-axis. So the vertical axis of the center of mass that we're measuring over here, quantified by accents. So they're really confident. They're moving. Look at this part here. Look at the knees now. See if we can pick up the next one, the knees. Yeah, right. So you have this bouncing aspect to it, where they're supposed to be quiet, right? Because there's this trial of the preparation and then the execution of it. See, whereas in contrast, this is your low expertise performer in here, someone who is doing it. They're fast, but they're not the top ranking fast, right? So you see if you can see. Right? Much slower, a lot less. And you see this, right? You get the gist of it. And so where I wanted to draw your attention on is these in between trial periods. that burst activity in there that we don't control. We tell them to keep still. So there are some sort of strategies that people are using that are like this knee sort of knocking effect, which shows this freeing of degrees of freedom. So this is what Nikolai Bernstein said. It's the same thing with ballet dancers, where you see them, they are not stiff and they move, but they're very fluid and they know how to sort of correct themselves when they sort of make a mistake as well. So how do we quantify that? Because these are supposed to be the uninteresting parts of the data. These are the parts that we tell them, keep still, prepare for the next trial. And typically you don't look at this kind of data. So because of the way that the task is designed, we have the prep phase and we have the modal phase. And this prep phase is a quiet period of 1,000 milliseconds, and we can learn a lot from it. And you have the modal phase as well. And it depends on how long is it. So some participants take about 3,000 milliseconds, some of them take about half the times, 1,600 milliseconds to complete the entire sequence as well. Yeah, so I wanted to quantify the differences, the behavior differences between high and low expertise, the fractal scaling differences in both the preparation and modal execution phase, and also understand the differences in this phase between the high and low learners. We had 22 participants, 6 of them were female, and this was some of the content. So bearing in mind, this was my earlier experiment, so we really made them learn a lot. This was, wow, 480 trials, so I think that's double the amount that I explained to you. So 2,560 sort of steps altogether. So by the time they finished the 10 blocks, they were quite tired. We have a test phase whereby in the last 2 blocks, one was a familiar, they always perform a familiar sequence first, and the very, very last block was the introduction of 2 unfamiliar sequences. And how we categorized was based on the performance of the 10th block. We would say whether, and rank, we did a rank based on rank the participants and their RT, and the top 50% would be considered the high expertise group, and the bottom 50% would be considered the low expertise group based on only the accurate trials in here. So let's look at the behavioral data first of each of the participants. You can see this is the accuracy of the performance. Sorry, it gets cut off over here. So can I click OK? Yes, and it goes away. Yeah. So just by looking at the accuracy, it stayed very, very much the same. There were no significant difference between the accuracy. Both groups of the high and low expertise were as accurate as each other. It's just towards the last block where the new sequence was introduced, you had an interaction effect in there whereby the high expertise group, people in the red, stayed the same, but the low expertise people start to drop off. So there was some sort of change when they were dealt with inaccurate sequences. In terms of response times performance, you can see in the gray box, this is again the low expertise, always in gray. Sorry, the next couple of slides are the low expertise, and the colored ones are always the high expertise people. That high expertise from block 1 alone produce much shorter RTs compared to the low expertise learners. So there you already have that behavioral differences between your high and low expertise groups. But let's look at the Hertz exponents across the blocks as well. So here we extracted the prep phase, which is that 1,000 milliseconds that you looked at, that preparation phase, that phase where you saw that participant doing the knocking of the knees like this. And we modeled that entire 1,000 milliseconds against each other for the 10 blocks. There is a significant linear trend increase for the high expertise learners. You can see for all the 3 directions, X, Y, and Z for the center of mass, for the acceleration. And this was not evident for the low expertise group. So you see this increasing of Hertz exponents towards 1. Okay, remember we mentioned that values that are closer to 1 are showing participants that are more adaptive and more fractal in their behaviors. Contrastly, in the modal phase, you will see that in the X, Y, and actually the Z direction as well had a significant decrease in the fractal scaling. So instead of approaching towards 1, it was going down away from 1. A bit contradictory, right? Towards what I just said earlier, the higher fractal scaling components represents a better performance, right? So what's going on in here is very, very interesting. The noise that we look at, the period of the preparatory period where we consider as usually noisy tells us a lot. That increased fractal scaling components tells us that preparedness and how it increases with developing expertise. They're able to more accurately anticipate what's coming up ahead. So fractal scaling goes up. It requires more energy metabolically for the entire body, including the cognitive loading of the memory, etc. But once it's goal time, that whole motor execution, there's a decreased fractal scaling. So it tells us that there is no need for us to continue to keep that high fractal component because it's really costly. It's this fine balance when you look at the fractal and what the literature suggests. It's this fine balance of what is considered chaos and what is considered like regularity, or in another way they put it is through exploration or exploitation. So where you can save energy and where you already know something, the fractal scaling doesn't require that. You don't need it. You just execute based on the memory that you already have of the sequence, you see. So this is very interesting for me because when we first saw that kind of data, we weren't really knowing how to quantify that noise components. I know that Julian himself is also very interested in some of these noise components within the attentional part of it. So I'm wondering if we can apply something like this to look at the fractal scalings. Let's see. Right, so that's my first part done. How can neuroimaging then help quantify differences in individual learning performance? Here I'll start to draw upon Williams' very famous now sort of framework, which he considers he calls it the cognitive framework for sequential motor behavior. So there's an assumption that there are several different kinds of processes within our motor system. One is the perceptual processor, where we just try to identify what incoming stimuli is towards us. And your central processor is the one that, imagine these are sort of fictitious entities, but your central processor is the one that takes note of these stimuli and tries to make and formulate a symbolic representation of it as well. Now, they're gated by what we consider as the short-term memory, okay, which is considered a limited resource of about 7 plus minus 2. Okay. We can have a lot of debate about this. We can do it afterwards if we want, but then I'm just following the literature so I can continue with my story over here. And of course, the motor processor then steps in when we need to replicate or produce the sequence itself. So M1 takes over and this becomes effector specific. So if you learn something with your hands, you are very good at producing with your hands, and sometimes there's some sort of transfer over to your legs as well, or inter sort of hands as well. So they can be they are developing these response-to-response associations. So this is the framework that we're working with. And as you learn a task, as you learn a model sequence, you become better and better at it. You go from a reaction mode to an associated mode to therefore a chunking mode as well. So chunking is where you start to piece things together, right? Three items, 2 items, 4 items. How do you remember your phone number? 060 175 444 16. So that's what we consider as chunking. And it's a behavior that shows up when you become very efficient at a task as well. This is something that's also really talked about a lot, whereby there is a cognitive cost. So whenever we have these chunks, we usually remember the 3 items. So let's say, as I mentioned, my phone number, 060, that goes really fast. But when it comes to the next set of numbers, there is a cognitive cost involved in it, and that's what we consider a concatenation point. So the response time increases because we need to draw on this working memory again to inform us of the next part of the sequence itself. And this slowing is presumed to be the loading of information related to the next chunk of the sequence. If we then try to look at the literature and if we can quantify and say, look, is there a neurophysiological signal that we can track that often tells us of predictive short-term memory processes, we can point towards theta ERDS, which is event-related synchronization and desynchronization, especially if you consider it from the central sort of electrodes as well. So if therefore short-term memory is a binding cognitive function, theta is oscillatory activity should increase when we need to retrieve information related to the memory. And when I first got into University of Twente, I did one experiment whereby I just used the fingers. So this is not this data here. This slide here is not with the feet, not with the legs. Indeed, I did see that increase. So around the time point of the fourth key position, this was not very precise, but we can say a plus minus 10% difference. We can see that theta ERS is also positively associated with response times. So we see a spike. The two lines represent the gray line is the first learning block, and block 5 at the end of learning is you see a significant increase within this time point, and it coincides with the fourth key position as well. So I moved on from there and decided, okay, we can now measure, having inspired from meeting Klaus Graumann in Berlin, I said we can do this with EEG as well, and we can quantify what's going on in the brain a lot more accurately now in the foot task. And so this is our multimodal approach where we had a 22-channel anti-neuro EEG strapped on in the backpack, and participants were performing this 22 channels because it was just a limitation of the cap that we had. The cap itself in our lab is a combined cap with FNIRS, so there was not enough space for more electrodes. It's just the other spaces were for the FNIRS. I didn't measure FNIRS in here, just the EEG alone. So we tested the feasibility of it. I wanted to understand at the individual point, what is the difference between learning and concatenation, and wanted to see if we can quantify individualized approaches to sequence learning. Here in this pilot, in which Johannes here was part of the data collection team, and he did his bachelor's thesis on it. We collected 12 participants, and we had 4 blocks with 2 test blocks as well. 4 learning, 2 test blocks, 192 training trials in total. Still the 6 key sequence, So data pre-processing and analysis. So here I'm just looking at the C3 channel that's over the left motor cortex, and we filtered the data, ICA corrected it, and also we epoch the trials to capture all 6 steps. So you can imagine this is a very interesting thing because some participants that I mentioned, all 6 trials takes about 3,000 milliseconds, and some took about 1,600 milliseconds. So we also applied a dynamic time warping approach whereby we were able to take the data that's occurring at one of the steps and also the data points that are around that step, and after that bin them in together as well, so that we have a sort of modified dynamic time warping approach to still capture the theta activity that is surrounding that steps with quite a lot of certainty. And then we stitch it back up together so that we have a relative amount for every participant that is a representation of all the steps. So this is, and then after we perform learning curve analyses to understand individual differences and linear mixed models effects for understanding the concatenation mechanisms. So the group behavioral results show that the majority of the learning already occurred at the first to second learning block. Every subsequent block after that was sort of a refinement of the sequence. They were not learning as much as what they gained from going from block 1 to block 2. That was the only significant difference within the RT of the behavioral data. So this is the group. Then remember that I told you that at the 4th position, with regards to motor chunk concatenation, you often see a bump, right? So we don't see that bump anymore. So there's something very fundamentally different from the step task, from the dance task, compared to the keyboard pressing task. All right, the affordances are quite different. Perhaps the way they're using the memory is also different. That was my sort of suspicion in here. So we don't see that task in which they have that bump in the 4th position, or the 3rd position, or the 5th position. Everything became the sort of as fast as each other for the step positions after the first step. So for me, just behaviorally, if I stop here, I would say that they loaded the 6-item sequence at the goal. They didn't need to load a second part they didn't need to split the sequence into 2 parts. They only needed to have 1 part of the sequence, and that was a clear representation for them. If I stop here with the behavioral. No usual concatenation. So what I realized when I look at the theta ERDS results across the groups is that we do see a concatenation. It's very interesting. The peak of the theta synchronization happened progressively. So at the first block, it was at the fifth step. At the fourth block, it was at the second. At the second block, it was at the fourth step. At the third block, it was at the third step. And by the time we reached the fourth block, the final learning, everything was a lot more efficient, right? There was a lot less synchronization across all the different steps for the entire block as well. So the theta peaks suggest that memory is still cortically consolidated while the body is already doing its own thing. Okay, so you already don't need, the body is executing automatically with automaticity, but the brain itself still needs to consolidate the information in there. I was curious about the individual learning performances as well. So I looked at two very distinct individuals. Participant 7 over here had very, very nice behavioral learning curve. So you can see that it just falls nicely from a very, very slow sort of response time, ending up very, very quickly with high accuracy as well. Conversely, participant 5 is a lot more flat, and you can see the data points everywhere. So just looking at that, we would say that 5 is a poorer learner with lower expertise compared to 7. You can quantify that as well by extracting the amplitude, the learning rate of which each participant is going through, and also the asymptote, which is the potential final learning point of the person. So this is predicted to be around 188 milliseconds for each step, whereas this participant is still hovering around the 558 milliseconds for each step. So what's going on here? Why such a large difference? And recall that when we group the data, everything gets lost. This kind of very individualized, very key information gets lost as well. We have the phenomena, but we don't have the differences in the strategic performance of each participant. So looking at the behavioral results, you can see that that's different already. The way they approach it, remember the concatenation that I talked about, that hump? We have the high expertise in the light blue over here, going that same pattern as the group data, whereby every step after is really the same speed. And that was evident from the first block compared to the fourth block over here. So that slowing of the last step was seen. So these three positions were significantly different from each other for the slower participant, in that they increased while the participant 7 sort of maintained their speed throughout, see? And then if you look at the subject by step and block interaction over here, with regards to the theta synchronization, you have in block 1 a real large increase of theta synchronization, again at the C3 electrode for the low expertise subject 5, whereas the peak of the synchronization was at the fourth step, and then they sort of subsequently lowered that in the first block as well. By the time they finish the fourth learning block, both synchronization was similar to each other, except for the sixth step position. So they were similar for each other. So what can we say? All right, let me conclude this slide as well. What's happening is cognitively, both participants were already maxing it out. Okay, cognitively, both participants, the high expertise and the low expertise person, is already maxing it out. But behaviorally, there was a difference in how they approach their strategy, you see. So how can we help the individual learner? How can we give meaningful feedback to them? First is that the key takeaway is that there is no usual concatenation point, which suggests that the learners prepare the execution of the entire sequence rather than two separate motor chunks. That was already clear when that slide came up. There is also a temporal shifting of the theta peak, which suggests that there's changes in the activation of memory boundaries. So you're able to pull that kind of information earlier and earlier as your learning became as you had more learning. The individual learning curve analysis showed that they both had different learning strategies, but converged in their learning theta activity. So both were already executing at their cognitive potential for self-select strategy. This is the thing that gives meaning to the learning. How we can tell people individualized advice. So one is that for the learner 5 is that you need to continue to practice the current set of sequences, and you need to refine your strategies. Let us help you with refining your strategies. So that's the key takeaway. The second is for learner number 7, who is the high expertise learner. We say for you, let's move on to harder sequences. Let's go to sequences of 12 steps. Let's go to sequences of 18 steps as well. So for us, I really want to work towards being able to give individual advice with this without needing a one-on-one coach to point out some of these points as well. And if we can leverage on Mobi, if we leverage on the data, if we leverage on uninteresting information that traditionally we are discarding away. Usually we don't look at this kind of quiet periods to formulate this kind of advice. I think that is really pushing the field forward in terms of modern neuroscience. So yeah, potential collaborations. Today I had a look at the grail with Julian. I was very happy with it, and we already came up with some very cool ideas on how to embed sequences within the stepping at the grail, and we hope that we can write up quite a nice grant to proceed and win the money, of course. Yeah. Thank you. So many thanks to my students, Victoria, Johannes was here, Marcel, and Jonas. By the way, all German. They're hard workers and they're intelligent. So what can I say? None of them were Dutch. So thanks again. Any questions? Yeah.